Hi, my name is Manasseh Ephraim. In this video we will see a couple of examples of an integration technique called substitution. Sometimes people refer to it as U-Substitution. To just give us a little introduction, let's just say we have a function h that is a composition of two functions f and g. So I assume h of x equals f of g of x. And if we differentiate h, then what we get is, using the chain rule, f prime of g of x times g prime of x, which means that if we reverse the process and integrate f prime of g of x times g prime of x dx, we should be able to get h of x plus c, or f of g of x plus c. What's going on here is that if we look at this expression g, its derivative is sitting here next to dx. So if we call this expression u, then this is going to be du. So then eventually we get f prime of u du, which is integrable. That's basically what it is. But let's have an example to illustrate all of that stuff. So I have an example. I want to integrate sine of x squared plus 1 times 2x dx. Okay? Well, as you can see, I have a function x squared plus 1 inside of the sine function, and I set it up so that its derivative is just sitting out here. Okay, let me fix that one. I don't like this 2x. So sine of x squared plus 1. Sorry. Sine of x squared plus 1 times 2x dx. Okay, so now if I let u be x squared plus 1, then du by dx, the derivative is 2x, or the differential du is 2x dx. At this point I usually solve for dx, which gives me du over 2x. Okay? This step is usually skipped. Once we write u, we just go ahead and write du, which is 2x dx. Usually that's how people do. And now the integral of sine of x squared plus 1 times 2x dx becomes the integral of sine of, well, x squared plus 1 now is u. I'm going to put u in for x squared plus 1. I'm going to just put 2x as is and replace dx by du over 2x. Okay? And now, as you can see, the 2x cancels, giving me the integral of sine of u du. And that integral is negative cosine of u plus c. But u is x squared plus 1, so I'm going to put x squared plus 1 in for u. Then that gives me negative of cosine of x squared plus 1 plus c. And this is the integral of sine of x squared plus 1 to x dx. To recap a little bit, so you let u be this expression, which you would hope that the expression would reduce to sine of one little variable. And once you get u, write du as the derivative times dx, and then dx is du over 2x. And you put du over 2x in for dx, and that will reduce the expression. Now, let's have another example with I have the integral of the integral of x squared times x cubed plus 2 x cubed plus 2 to the fourth dx. Okay, well, what's the derivative of x cubed plus 2? The derivative is 3x squared, which is really close to being x squared with only a difference of a constant multiple, and that we can handle that really easily. So let's let u be x cubed plus 2. Then du becomes 3x squared dx, and solving for dx, that gives us du over 3x squared. And now I will put u in for this expression and du over 3x squared in for this expression to get x squared x cubed plus 2 to the fourth dx equals the integral of x squared times u to the fourth times du over 3x squared. And as you can see, the x squared cancels, and leaving me with the integral of u to the fourth over 3 du. But as you can see here, 1/3 is a constant, has nothing to do with the variable u. Okay, so you can pull out that constant and get u to the fourth du to integrate. That gives you 1/3 u to the fifth over 5 plus c, which is equal to 1 over 15 u to the fifth plus c, or 1 over 15th. U is again x cubed plus 2, so I put x cubed plus 2 in for u to the power of 5 plus c, and that's it. We're done. Okay, one more thing that I like to mention is that once we make our substitutions, if our calculation is right, if our substitution is right, if our choice is correct, the expression we get at the end is this expression here. Let me see. I lost my... okay. The expression we get at the end, this expression, is much simpler to integrate than the original expression. And not only that, we don't see any x's in this expression. They're all u's and du. That way we know that we're in the right direction. Our calculation is correct. Well, thank you. In the next video, we're going to do integration by parts. Okay, goodbye.